Welcome to a brand new series of Inklings, launched aboard the PSLV C-52 and on February 14, 2020 at 5:59 a.m. IST from Sriharikota, India. The first nanosatellite from the InspireSat program, InspireSat 1, began its journey to the outer space and into some fascinating questions of science and engineering during its inception in the year 2016. The INSPIRE program is a joint venture by universities from across the globe coming together to carry out space science missions while also building academic programs to extend the study of space science and engineering. It aims to provide a constellation of Earth and space weather observing satellites and develop a university microsatellite platform to address some of the outstanding questions in quantifying climate change, atmospheric coupling processes, and space weather effects. Joining us today is one of the principal investigators of this INSPIRE program, Professor Amal Chandran. Alongside, joining me as co-hosts for the day are Ankit Verma and Anant Kumar, who as students have been part of the INSPIRE program and have contributed to the design and realization of InspireSat 1. So before we talk about the details and the actual science that is happening with the InspireSat 1, which was recently launched, can you tell us in a very layman's perspective what essentially is a nanosatellite and what is the big science that we are aiming at with such small satellites?
Thank you, Shreya. Thank you for inviting me to come on this podcast. It's wonderful to be here and talk to you and the rest of the hosts as well. A nanosatellite is, I would say, a smaller version of a larger satellite. It's got all the components of a larger satellite, but essentially the development time and the risk that you can take with a nanosatellite is higher. And it was initially, you probably know that it was launched as a teaching tool for teaching spacecraft engineers about the process of building a satellite. But now we've started to realize that, there are, with miniaturization of sensors, miniaturization of communication devices, that these are capable of a lot more, right? I mean, as long as we get creative and ingenious with how we can design the science or industrial applications that can be made from nanosatellites, these are very efficient tools. And then, the good news is that you don't really need a dedicated launch vehicle to get them into orbit. So you can put them up and start getting really essential, really useful science as piggybacks. So it's low cost, it's faster development times, it's a single string, so no redundancy. But it helps you take a lot more risk with spacecraft building.
Ah, okay. That makes a lot of sense.
That is a good insight in general of a nanosatellite program. Coming to our INSPIRE program and the InspireSat 1 also, what is unique about this model, the INSPIRE consortium, and how it is different from other universities who are also trying to build their own nanosatellites?
Yeah. So I'll give you a brief history of how the program started to answer that question, right? CU Boulder has been making satellites since, I think we built the first CubeSat that got really good science. And it was not NASA funded. It was actually funded by the National Science Foundation in the US. And the funding came in 2010, the year that I graduated with my PhD from CU Boulder. So two of the, I think, cornerstones of INSPIRE, one is myself and one is Professor Lauren Chang in Taiwan. And we were graduate students at CU Boulder between 2005 and 2010. And we took a graduate projects course so the first nanosatellites, I think, went up in 2003 or 4. And, it was a curiosity at that time. Nobody thought we could do science. And NASA was really not into nanosatellites. They did not want anything to do with it. They were like, and Cal Poly and, there was Pumpkin having these CubeSat kits at that time, which was essentially, some PIC processors and, very basic 8085 pop processors on boards and, very basic architecture for what you could call a satellite, right? But these were, teaching tools, and NASA did not want anything to do with it. So we proposed a mission where you could actually put a radiation particle detector, right? and get like charged particles near in LEO, near Earth space, right? So NSF funded it. It was a very low cost project, and the engineering division at the Laboratory for Atmospheric and Space Physics, which is one of NASA's prime university contractors that build science instruments for interplanetary spacecraft, they really did not want to fly it because we have 100% track record of everything being successful. And the engineering director called Rick Cornert, who was the principal systems engineer, and said, should we even fly this thing? Why don't we just put it together as like a flat sat and tell them, hey, we built this, this thing, this is what it is, right? So Rick said, no, we have this is a flight program. We are going to fly it. So they put it together. And, it was UHF, right? I think it was 9.6 baud per second or even lower. I don't remember. But essentially, pumpkin hardware along with stuff that LASP built with students. And it was a spinner. It had a permanent magnet attitude control system, right? So you align it as a magnetic field and spin. So no active pointing, no high data rate communication, but it went up and it carried a really good particle detector. And you won't believe there are 25 peer-reviewed journal publications from that CubeSat, including one Nature paper. Nature is like, the gold standard for publications, right? There are many full satellites that have not had a Nature publication, and it got one Nature publication of what we call cramped electrons near Earth space. But, it was well designed scientifically. We've had CubeSat since that has not matched this CubeSat scientific output. But once that happened, NASA started taking a look at this and said, oh, okay, CubeSats can do active science. So the University of Colorado, I would say, had one of the earliest track records of getting good science from CubeSats. And, I'm from Trivandrum. And I did my PhD at CU Boulder, and I was working at LASP, and I visited IAST, and my research area was in upper atmosphere science. And I gave a talk at IAST, and I came back and I talked to our engineering director, who had also visited IAST as part of a Lockheed Martin group for interacting with Indian space ecosystem. And we kind of sat together and said, IAST is pretty nice university, and I think we can really build satellites together. So the IAST director invited us, and we talked about the program, and then he basically said, if we build something together, we can launch it. So that's how Inspire really started. And I talked to Lauren, who was trying to put together a program in Taiwan for building nanosatellites. And we thought, we can export that model of having students work on these projects with mentorship from full-time engineers who are experienced. So that's the key part, right? Because you let students do it, students will do really nice job on designing and architecture, but there is no closure. It'll just keep going on and on. So a program needs to be focused. A program needs to have a timeline. A program needs to be like, you need to know when to freeze the design, and you need to know when are you planning for launch? What are your science objectives? You can't try to get everything you can from the CubeSat, right? You have to be like, okay, it is great if we could do that, but we are not trying to do that here. This is our minimal goals, and we're going to do this. So that's where I think the full-time experienced engineer support helps. So if you have that mentorship and then you can structure the student team around, you can actually execute it. So I think that's what's most unique about the Inspire program, that you have these experienced engineers from these different universities and associated agencies that are helping out. But most of the work is carried out by students.
That's actually one of the quite key features of the whole InspireSat program, having so many students involved and, series after series, passing it on through the time. Sir, on this, I'd like to ask you, as you said that for nanosatellite, it's not like a big satellite. You have to miniaturize everything, literally everything. And you have to be very particular about because you cannot do all the kind of science that you want to with a nanosatellite. So in a very brief, can you give us an overview about what the process entails, like from, pitching up the idea to how do you actually send it up there to do the actual science that you're planning from the start? So just a very brief overview.
We start out with a science idea, and we start out especially in Inspire, we start out with, is there a launch available? And usually the answer to that is yes, it is, right? I mean, ISRO usually has piggyback space if ISRO is covering the launch. I mean, it's also worth noting we've had 2 launches from SpaceX. Inspire 2 and 5 went up with SpaceX. So launch is the primary question. And second question, how in, is it a 3 view? Can it be bigger, right? That's the second. And okay, so now we are mass and volume constrained. Now we look at, what kind of instrument can we put on with those constraints and what is available. Are there PIs who have these instruments funded, who can bring these in onto the table right away? Is there a tech demonstration that one of the participating universities would do? Do they have funding to realize that? And if the answer to those questions are yes, then we put the concept of the mission together. Right. And once that is done, we move forward with a preliminary design, and then as the money, people start getting funded, then we start putting the hardware together. So that's essentially, in a nutshell, of how one of the missions comes together.
So Amal, just following up on that, could you highlight with your experience in Inspire some of the key challenges that you, in the process of developing a small satellite, as compared to the conventional bigger satellites, as well as what in your opinion are the major advantages? Like, as you highlighted, there were some even nature publications. So what in these small satellites you feel that contribute to such good science?
Very good question. So I'll talk about the challenges first. So one of the key challenges, I think Ankit and Ananta, I don't know if you are familiar with this, but Kaustubh certainly is, because the first instrument that was proposed to go up on InspireSat 1 was an infrared imager that was going to get phenomenal science, but was a very, very challenging instrument to put. So we needed to operate the detector at about minus 30 Kelvin. Minus 30 C. So we needed to have a cryocooler on board, and it was a very challenging instrument. And the instrument design was not at a stage where we could actually go about building prototyping the instrument. So we had to actually descope that instrument and put the compact ionosphere probe, the instrument from Taiwan, on board. So the initial concept of InspireSat 1 was to fly this infrared imager. And then we realized a year into it that this was not feasible, right? So you had to make that programmatic decision of descoping that and putting CIP on. And then we made another programmatic decision of adding on the solar X-ray instrument. But why did we add that on was because, during the CIP instrument was only making measurements on eclipse, right? And during the sun time of the orbit, we were going to point at the sun. And the X-ray instrument is just staring at the sun. So it made sense that, during the sunlit portion of the orbit, now we have an instrument that's going to get science data without any extra, concept of operations required on the satellite. Right. So we added another instrument. Now that's kind of the primary instrument. But of course, the concept of operations did change quite a bit, but programmatically it made sense, right? So in a larger satellite program, this kind of flexibility is completely out of question. You cannot do it. Right. On a small satellite, on a nanosat program, you have the flexibility and adaptability to make these kind of changes. Right. So we went from a 3U, the initial, the stickers and the emblems we had was a 3U satellite, right? We went from a 3U to a ring deployed satellite, the ring that Priyadarshan came up with one fine day and said, look, we are going on this. And I was like, what? Right? So we went from a canister deployed satellite to a ring deployed satellite, and we grew in size to a 12U. From a 3U. So we grew 4 times, fourfold. So those are, this is a challenge, but we turned that challenge into an opportunity, right? Because we found that the ISRO 3U deployer was actually 40 millimeters smaller in size than the P-pod deployers, which we designed the 3U to. So we found that we were not going to fit within the ISRO 3U deployer. And then we went to the ring deployer. So we grew in size and we accommodated one more instrument. So the challenges also present an opportunity with nanosatellites, which are not really available in the larger ones. And then your second part of your question was, what are the science, right? Advantages in science. So, it's very important to note, Anand, that the science has to be very carefully thought about in nanosatellites. Right. Larger satellites have fewer advantages. And I'll bring out the example of CIP for CIP. I'm not sure how good the CIP data would be. Okay. And that's because it's a plasma detector, which is going to be really affected by the spacecraft charging. So on a nanosatellite, in a charged environment, the whole spacecraft is going to have one charge. Right? What is Earth on a spacecraft? Your grounding, your neutral potential, we don't know. So the spacecraft charging is probably going to affect our measurements, right? On a larger satellite, you can put a boom, you can put the Langmuir probe on the boom, and then you can get much better data, right? But you have to be really careful about what are the science objectives you're going to get. Right, and design it. Now, those instruments have the X-ray spectrometers and the X-ray images that are getting all these flares. But we are carrying a spectral, we are carrying a detector with very fine spectral resolution, right? So we're getting these photon counts. And getting the photon count information down is really, we're not imaging the sun. We're just getting photon counts on these narrow channels. So you can get really good spectral data that way. So you have to be very careful with how you design the science. And that, I think, is the key part of what constitutes science on a nanosatellite.
Thanks.
It makes a lot of sense. Sir, while you're moving further into the technical bits, can you tell us, during its conception, while you were dotting down the whole program for the InspireSat, what were the milestones that you people were looking forward to? Like, you tell us that you had to impromptu change the actual things that you were planning, and it just happens in a click and since you have nanosatellite, there's a flexibility attached to it. So what were the milestones that were dotted down and planned, and what are the milestones that are being achieved at the moment also?
2016 was when we kicked off the program. We had a summer program in Taiwan. None of us were funded at that point, right? So Kaustubh, I remember very, very fondly now, standing up. Priyadarshan couldn't attend the meeting, Professor Priyadarshan from IST. I think he had some issues with his visas. So he could not attend. Kaustubh attended, and he stood up and said, IIST will build the CNDH. And we were all very impressed because he was like, he was taking on all of these things for IIST, and he said, we'll do the EPS also. And they did, right? In the end, it ended up that IIST did those things, right? But it was very impressive to see a student take charge and say, look, we're going to build it. He didn't say, I have to go consult my professor, because we were saying, if we're going to build this, who's going to do what? And he took charge at that point and said those things. And then, the milestones were that we were going to start work in 2017. And 2017, we had the first workshop in Boulder. And again, it was conceptualized to fly the other instrument, or, it was a 3U. But I would say work on the satellite as it was started basically in 2018. So we have summer programs every year in Boulder where we get 10 to 12 students. So the end of every summer program is a milestone. So the end of the first summer program in 2017, we had PDR. 2018, we had CDR, critical design review. And then 2019 was supposed to be, December, we were supposed to deliver the spacecraft. 2019, end of the summer, Ankit was there for, I think, for 6 or 8 months in 2019. We had nowhere near ready. Our EPS was all over the place. We were on EPS revision 2, and we ended up flying EPS revision 5. So between 2 to 5 happened within 6 months, by the way. So, there was quite so 2019 was supposed to be environmental test review, and that didn't happen at the end of 2019. So 2020 March is when we did Vibe on the spacecraft. So that was when, I was in Singapore. I came back from Singapore in February. This was when Corona was, going everywhere, right? And March, we had Vibe, and the next week, Colorado shut down, okay? And then we had TVAC in June of 2020. June of 2020, we did the TVAC, and after that, we had the fully qualified space system, right? So we were ready to deliver after July of 2020. Really. And between March, April, May, and June, a couple of months were basically wasted because we couldn't get to the office. But it was pretty impressive that, by the time that I think Ankit left in August or September of 2019, and the satellite was nowhere near ready, and we pretty much rewrote the entire flight software also. But getting that ready to 2020 June was pretty impressive. We were able to finish it. So those were the milestones. So in future InspireSats, and I hope you guys put some pressure on Priyadarshan here. We have InspireSat 3 coming up. Okay, so NASA has funded an instrument on InspireSat 3. And so, LASP is fully funded to build it. I think IAST is providing a thruster and some parts, and we have the spacecraft coming from Singapore. So most of that is all, funded. But I want PDR to be end of this summer. So I want the student program to start 2022, right? So PDR end of the summer, CDR end of next summer, and hopefully we get to flight in 2024. That's the goal. So, an Inspire satellite should ideally be a 3-year program. And I think next generation should be easier because we have some heritage in the hardware. So we don't need to start from scratch on a lot of things.
Yeah, just following up on that for the knowledge of others, for InspireSat 1, I know of the milestones it has reached, but could you just tell everyone about currently where it is at and what are the things we are looking forward to? For
InspireSat 1, Anand?
Yeah, for one. Like what it has achieved so far in orbit. Yeah.
Right. So, so just following up on that story, right? PDR was 2018, CDR was 2019. We started prototyping and building out the spacecraft. 2020 March, we completed it. So this spacecraft, as it was built, was completed by March 2020. Right. So the spacecraft is actually 2.5 years old. I would say 2 years old since complete integration. Right. And then environmental testing in June of 2020, we had a battery anomaly, which was essentially a fire inside the spacecraft in December of 2020. We had a transient from, the battery shorted to ground and essentially, was on fire. So we had to take it out. None of the other systems were thankfully affected. We took it out, we swapped out the batteries, did another environmental test and shipped the spacecraft to India June of 2021. And then the satellite went up February 14, 2022. And it's been more than a month in orbit. We have received, I think, more than 25,000 beacon packets from all of our ground station in about a month. We have turned on the science instrument. We have observed an M-class flare, which is a really good flare. We've downloaded that data, and we have about 5 or 6 C-class flares that the DAX instrument has seen. And so we, I think, have enough data for publishing already. And a couple of papers probably from the spacecraft in a dawn dusk orbit. Not many CubeSats get into a dawn dusk orbit, so we are always seeing the sun. The spacecraft was not designed for a dawn dusk orbit. It was not designed for a sun synchronous orbit. It was designed for a mid-inclination orbit. So in a sun synchronous orbit, you get more charged particle hits. So I am still quite concerned about our spacecraft being in a sun synchronous orbit with all these exposure to charged particles, especially now when solar activity is ramping up. So seeing all these flares is great, but it also means that you're getting more charged particles than high energetic particles coming from the sun. That's why you're seeing these flares, right? So it's a double-edged sword. You see a lot of flares, but you might get a lot of particle hits. So far, so good. The spacecraft seems to be very robust. We've not had a charged an ACU incident so far. So knock on wood, it stays that way. But spacecraft has been really, really healthy. We will probably, fully commission the spacecraft in a week or two. and we should be able to get, S-band high data rate downlink, and that's probably when we'll say it's fully commissioned.
Yeah, I mean, we were all really excited when we got the first science spectrum and the various data. Yeah.
Yeah, we made the NASA science highlights for last week, actually, last week or 2 weeks before. So yeah, they put the spectrum up, and I actually had a call with Dr. Madhulika. She is a very senior scientist at NASA. She's a heliophysicist. She's the program lead for Living with the Star. And she actually called me and said, look, I've been trying to fly a NASA instrument on ISRO for a long time, and it's never happened. So she didn't know about this. And she was like, how did this ever happen? Because this is the first NASA instrument actually on an ISRO spacecraft. So I think we've achieved a few milestones, but it's a CU Boulder instrument on an IAST spacecraft. So I think a lot of collaboration is possible if we leverage academia.
Right. So just one question I had. So you mentioned the solar flares we studied. So how were these science questions basically decided? I mean, what I mean is, did a lot of scientists, solar physicists and atmospheric physicists sit together and say, these are the problems we want to solve? And how were these, packages conceptualized that this is the particular instrument we want to fly? And
So good question, Anand. I think a lot of these science questions and a lot of the instrumentation is driven by individual scientists, right? Individual scientists who kind of address the open questions of, what are the measurements we require to close out some of these open science questions, right? So if you look at the solar X-ray spectrum, there are parts of the spectrum which are not captured from the ground because, these waves and these frequencies get absorbed by the upper layers of the atmosphere. Right, so you can't see it from the ground. So you have to do space observations. But then, all your GOES instrument or your other instruments are not looking at this particular part of the spectrum. But then, the instrument that we are using is actually used for detecting X-rays from rocks. So it's not designed as a space instrument, but it is sensitive at these spectral ranges. Right. So Tom Woods, who is the principal investigator on this, took these commercial off-the-shelf X-ray detectors, space qualified it. Basically, he put some extra shielding on some of the components, put it in a vacuum chamber, look at the residual gas analyzer to make sure it's not outgassing and going to clog up other stuff. And then basically space qualified it, flew it on a rocket and saw the spectrum. So that was the first step. And after that, he proposed that as a CubeSat instrument, right? So he got that data, and the same instrument is actually being flown on Chandrayaan-2. So there is a really good heliophysics group at ISRO, and Tom has been having discussions with them. I think the ISRO and LASP solar group meets once a month or once every 2 months. And they've used that data to cross-calibrate with the instrument flying on Chandrayaan-2. And a similar instrument is scheduled to fly on Aditya as well, right? And then Tom actually used a new concept with a dual aperture. So it kind of filters out some of the other lines as well and gets very high spectral resolution. So the spectral resolution we are getting from the instrument on InspireSat 1 is about 4 times better than the signal to noise ratio and spectral resolution we were getting with MINX. So that's why I think they could see these different spectral emission lines very clearly from, I think, neon and iron very clearly. So these are elements. So each of those spectral line emissions correspond to an element in the solar corona. And these solar corona elements can change at times of a flare. So you get, spectral line shifting based on the composition of the elements. And what this is telling us is about how the corona behaves and why do these spectral elements change. So it gives us an understanding of the coronal heating processes.
Okay.
And that's what we say. So basically, I would say it really depends on the scientist, the instrument scientist. We know open questions, right? So we know what part of the science needs to be addressed, what are the measurements we need to be made, and then it's the the creativity of the instrument engineers on how can we make those measurements.
Right. That's very interesting to know. And then just a question on the administrative side. So how is it for you running a satellite program as though it wasn't hard enough, and that too in 3 separate time zones, or I guess even more than 3? And what were the challenges you faced on a personal level?
It was pretty challenging. It started out as something that I thought I would be doing on the side, just doing one satellite with IAST, right? On the side, maybe 10-15% of my time. That's what we really envisioned it for 20% of my time, which was 1 day a week, right? 20% of my time. And I would be on other projects for the rest, but it quickly became my full-time job running this program, which makes sense because you really need somebody who is focused to keep all these little different bits and pieces together. I mean, if you look at Professor Priyadarshan, he probably had so much stuff going on with his teaching and all of that he really couldn't manage it on a day-to-day basis, right? And I took up a job in Singapore, I think 2017. And basically they wanted to put satellites doing space science. So I got funded for 3 missions. So InspireSat 4 is supposed to go up next year. And then 2 student satellites, 3U student satellites at NTU. One is supposed to go up this June with the PSLV C54. So I am headed out to Singapore in a couple of weeks for the environmental testing of that satellite, and we deliver that satellite in May. So that's a 3U. And then another 3U is supposed to go up next year as well. So 3 satellites there, and then this one. So, it became really busy to manage all of this. But this is what, you sign up for, and it's exciting work, building satellites and hopefully getting good science done. Inspire 4, I'm really optimistic about because we have an infrared imager, we have an ultraviolet imager, and a ground, a nadir imager. So, and we have electric propulsion to bring down the orbit to 350 kilometers and try to maintain that orbit. So it's kind of like low altitude flight. And we have the plasma payload from Taiwan as well. So yes, so it's 25 kg. It's a big satellite. It's it's a 27U 25 kg satellite. So it's exciting to try new things. It's exciting to build new technology, but then you end up working odd hours. My meetings usually start at 6:30 a.m. and go on till 11, or because of the different time zones. So that is the toughest part.
Also, sir, along the similar lines, there are a lot of permissions, across the borders, because when you're crossing a country, it changes, and especially when you're dealing with the space program. Would you like to share a personal experience, maybe where something you faced quite interesting, you found it in some sense?
Oh, there's so many. I mean, the licensing for InspireSat 1 was done from India. We talked about, licensing discussions started in 2018, I think. And of course, nothing happens till you deliver the satellite, right? So we were not sure when launch was going to happen. So I think one of the important lessons learned is that we need better communication from between teams. And I think the success of Inspire 1 is going to facilitate those conversations, because, we were building a satellite, but I don't know how many people in ISRO were really aware of this, right? So we had very minimal conversations with the launch team, right? And then finally, the launch team, when we had shipped the satellite, the launch vehicle team asked, can you send the fasteners so we can qualify the fasteners, right? And it's a fair question, because, how can they fly something? And if we use those fasteners, how do they know it won't shear and break? And then, you don't want your small nano-satellite going and breaking what the EOSO4, right? the imaging side. So, but those are the kind of questions and the coordination that you need to do in advance. And I think now people will realize that this is a full program where you actually can get good science from the student team and communicate much better with us, right? If we are building the ring, send us fasteners, we would have used those fasteners, right? ISRO spec fasteners. Other thing is radio licensing. the radio license, we are still not licensed to use the US ground stations, which is a shame because we have a ground station in Fairbanks. And if we had the US license, we would have had like 10 passes. If it's a polar orbit and you have a polar station, you can use that. But we couldn't get the IARU coordination. And then without IARU coordination, we can't use the US ground stations with the FCC licensing. So, there are a lot of lessons learned about how we could have gotten the administrative things done better.
Yeah.
But I am happy that we were able to do what we did, because ITAR and export control, people hesitate in the US to do these international collaboration because they don't understand ITAR. We qualified the whole program as fundamental research between two institutes of higher learning. And there is a fundamental research exemption that can be leveraged. So all the hardware we did was, Indian students can work on it, Taiwanese students can work on the hardware. So there was no export restrictions on the hardware, except for the attitude control system, which was a little problematic because, the company that sold it to us said, it has to be, you can't share the ICD outside the country. But when Anant and Ankit came and all the summer students came, they were essentially LASP employees. They had, they were J1 employees by LASP, and then we could share it. There was no international citizenship requirements there, right? So it was just restricted to LASP. So that was the problem that we had, but, it was...
Yeah.
We could overcome all of that. So it sets us up. There are a lot of lessons learned. We should, I think I should write a paper on that because it will help people.
Yeah.
That's actually
the answer is it's possible, Shreya. I mean, the answer to all of this is that, these administrative hurdles can be overcome and we can get these projects done, right?
Yeah. That's actually, I think, the bigger issue that people in science face, dealing with the administrative part. Because science they can do, but this thing can be a little... Another obstacle that I think could have been is, like, I would really like to know, how did you manage? Because the whole timeline of the project extends more than let's say, an undergraduate program or a master's program or even a PhD program. So how do you manage to ensure that the passing of the knowledge from student to student is efficient, or, you're not starting from scratch with every student that's joining?
That's a really, really good question, and it's a problem we have not solved. So when I said, that a project should be 3 years, that's actually within an undergraduate student lifetime, right? So Ankit was a second-year student when he first came. So was Anant, I think. So the idea was that we would launch it when Ankit these guys would graduate. So he came in his second year. And then, third and fourth year, we were supposed to launch. I think you graduated 2019, right, Ankit? Or 2020? Yeah. So we were supposed to launch end of 2019, but, unfortunately, we missed 2019 December. And then we were ready probably by 2020 July to launch. But then Corona hit and number of launches went down and we ended up in 2022. So if things go according to plan, if you have a second-year student coming in, by the time that student graduates, we should be able to get a satellite on board. So these 3 or 4 second-year students would form the crux of the program, right? They would be the core team, right? And you would have continuity till the end. We also tried to budget for a PhD student to be on the program, and that PhD student is supposed to be the lead systems engineer who knows the stuff. That is why, my involvement was going to be 20% 1 day a week, and the PhD student was going to do most of the coordination and overall systems engineering. Unfortunately, on our program, our PhD student graduated with a master's after a year into the program. So we lost that student, and that's why, I pretty much had to take up that role as well. right, to provide that coordination throughout the life of the program. But that's the idea, that you would have a graduate student who provides the systems engineering role, and the full-time advisors hopefully are well aware and knowledgeable about the systems that they can guide incoming students. And that's where having these full-time engineers is a big asset. I think at IIST, having Joji, for example, was a big asset. I would say that if IIST can get a couple of project officers on board who are going to be involved in the hardware side and retain them for 5 years at least, then that provides continuity as well. And the students can provide all of the supporting roles. So even if a student graduates and a new student comes in, they can come up to speed. The third thing is, of course, documentation. The documentation on IS1 was decent, I would say. We could have done better. But when I look back, there is fairly a good amount of documentation that people can read up and see about, how the design progressed. So it's not the best, but it's not the worst either. It was fairly decent, and there are quite a number of lessons learned on where we could improve some of this.
Yeah, so it does sound like the 3-year timeline does help with the continuity, at least within one undergrad duration. But there's one more aspect to this, that, for example, when I joined Inspire, I was a second-year BTech student, had no knowledge about our nanosatellite or anything. How do you even proceed with it? So no idea. At the same time, you have only 3 years, that too with your students who are completely inexperienced. So having this 3-year deadline is a bit constrained. Does it put too much constraint on the how fast or how reliable the nanosatellite is gonna be and the subsystems and stuff?
So Ankit, it's a fair point. I think you were thrown into the deep end when you came in, right? But ideally, we would really have. So the next generation of students that come into the Inspire series of satellites will have a much easier lifetime, because the moment they come in, they have working hardware. They have an avionics stack that works. That is the starting point. For the first InspireSat, we had to develop the full avionics stack from scratch, right? We did not even have a ground interface board, or the ground interface board, let's put it this way, was very flaky. I mean, we don't even know what was going on, right? Was it the CNDH board? Was it the ground interface board? Was it the software? I mean, just to give an example, right? Troubleshooting was, and how many weeks did we spend doing that, right?
A lot, yeah.
A lot, right? So the next set of students will have life easier, because almost they come in with a working stack and they are making modifications, right? But again, you're right. Training these students to get up to speed takes time. So when you are a second-year undergrad student with not much experience, that's when the full-time engineers and that's when the graduating students have to train you, right? And I would say that in your first year, you're not expected to be productive. You should not expect to be productive. You should be learning the system the first year, and you start being productive the third year onwards. So the third and fourth year are when you are productive, and by the fourth year, you're transferring your knowledge to the new incoming second-year students. I think we'll have a much better structure. Ideally, that's the way that it should have worked. But we have to start somewhere. You were ground zero, right? You were generation zero that went through the whole pain of having to develop it. And credit to you guys. You guys did really, really well.
That sounds good. I mean, looks like we are looking forward to what and all is going to happen in the Inspire mission now.
Well, I'm hoping that we can get Inspire 3 going. There are challenges, the challenges never end. We need solid support, right? I mean, ISRO needs to provide support to IIST. I mean, I think IIST has already built the space lab, which is a step in the right direction. And then Priyadarshan and the folks at IIST need to structure a program where you can bring students in. And Shreya, I think you were in the earth sciences, right? So you need an interdisciplinary approach, right? You need to take in students from all of these different departments. So you need to have a program where, IIST is a space science institute, right? This should be the flagship program at IIST, right? And you need to be able to get a crop of 10, 15, 20 students who are involved in multiple different projects, and ISRO needs to fund those projects too, right? So, and then you need to get more faculty. It should not all be on Priyadarshan. You need faculties, PIs who will come in and help support that. So if that is the structure you have at IIST, and similarly, I need a structure at LASP. I need, LASP funding so that, we have the summer program all funded, and we need facilities. Remember, we shuttle between CU Aerospace and then the biotech building, right? So yeah, I mean, it wasn't ideal, right? So we need space. We don't need to be refugees going between each department. So I have my own administrative hurdles at LASP where we need that space. We need that to be funded. And then like instrument bill can, it's a competitive market that we have to play with here. So we have to write proposals to NASA, and and NASA funded the InspireSat 3 instrument bill. So we are funded on that. But then, you need money to host the summer program. Just like that, NCU and NTU have their own challenges, right? So each university needs to bring in their own funding. And if we can get that support, this can be a very good program.
Yeah, it would be really amazing program. And we are looking forward to the next missions.
Yeah, well, I do hope Inspire 3 can happen, but at this stage we don't know. And I would really like this uncertainty to go away, that the funding agencies actually support it, and this uncertainty of can we even do it goes away.
Mm-hmm.
Okay, Ankit, do you want to take up the next question? Maybe the last one.
Yeah, so of course, in this session, we talked about the science InspireSat is doing. And as you mentioned, we have some spectrum for M level, M flares, and all those things. These are pretty exciting. And I'm sure, of course, I know that you are very much into the research of ionosphere and working as a LASP employee. But looking into the other direction of how Nanosatellite bus being cheaper to build and faster to build, how it can help academia to develop and demonstrate new technologies which can push the boundary of not only the nanosatellite, but also the big mainstream satellites too?
I think there are a lot of ways that we can do this. So I am actually, I don't know if you know of this organization called COSPAR. It is a Committee for Space Research. So COSPAR was formed during the Cold War era to foster international collaboration between countries. So I'm actually the vice chair of a task group on a constellation of small satellites. So COSPAR is basically playing the role of a facilitator. The idea of this task group is to facilitate building a constellation of small satellites for addressing open questions. So one of the open questions is, of course, space weather. I don't know if you guys know of this recent event where 40 SpaceX satellites burnt up in the atmosphere, right? And the reason why they burnt up was because there was a consistent solar flare and neutral densities increased, which increased the atmospheric drag. And SpaceX launched these satellites into a 250 or 210-kilometer orbit, and then they would use electric propulsion to go up to their designated orbits. The reason for launching low is because you can fit more satellites into one launch vehicle. But the neutral density is increased when these spacecraft actually deorbited. So one of the things the COSPAR task group wants to do is a constellation to look at neutral densities, for example, right? Because these neutral densities real-time measurements would then go into forecast models. So space weather forecast models, which would then give us a data product. So we are starting to use low Earth orbit space in a way that it's not been used before. Right. When you're looking at broadband internet from space and you're looking at constellations of 30 to 40,000 satellites, LEO space is commercial real estate. It's commercial real estate for big business, right? It's not even space. It's going to be enabling a lot of technologies in the future, right? GPS is a classic example. Everybody uses, Google Maps on their phones, right? But looking forward, internet from space, services from LEO is a big market, right? The space industry is poised to become I think a $3 trillion industry by 2040 or 2035. So if you look at those numbers, and things like small satellites can actually provide the space weather forecasting that we need. That's going to be, we take weather forecasting for granted. We are going to need much more accurate space weather forecasting. So that's one area. The second area, of course, I think that small satellites can really help with is climate monitoring, right? If you look at, say, climate change effects, if one of the big unknowns in climate modeling is what is the outgoing long wave radiation from the Earth. We don't really know. So it's a big unknown in the climate model factors, right? But you can get those measurements from, and that's what Inspire 5 is actually doing. So the French, the lab LATMOS actually put a radiometer that's looking at long wave radiation going from the Earth. And they've been pioneering this concept of putting a constellation of small satellites to measure the long wave outgoing radiation. So that's another instrument that would do wonderful science and can give, great data. So those are on the science side of things. But then if you look at the technology aspect of things, there's quite a number of things that can be done as well. So if you have, IoT devices in hard to reach places, storing and forwarding from IoT devices from CubeSats is a concept that can be used for monitoring illegal mining, monitoring, water quantity. So IoT to space from these remote regions, looking at ocean currents, ocean temperatures from buoys. You put IoT devices on buoys and then, use constellation of small satellites to get that. So it's like a LoRaWAN receiver, right? You can get those data from those small transmitters and then store and forward it. So there's quite a number of applications, industrial applications for CubeSats as well, that doesn't break the bank.
That's quite
wonderful. That is fascinating to see.
Actually, I could not imagine how many spares this particular CubeSat could touch, but it's wonderful to hear the number of applications that can be taken up from this particular project.
Yeah. I think it's so with the miniaturization of devices, I think it's a big aspect of, how can you build these simple satellites that would help with solving some of these applications.
It's like simplifying rocket science, essentially, in a massive way. But that's wonderful to hear.